All right, it is Friday, December 2nd. A lot of guys have already logged on to Kahoot, so I'm going to switch the screen. We'll go over and do that. We've got a fire drill that's just a drill. We're just sheltering in place here. I'll start the midterm review with the guys on Friday, so next Friday. Okay. Got some other labs and activities lined up for the next few days. You guys have this half page. You guys see this half page with 20 conceptual questions related to rotational mechanics and stuff. Hey, guys got it? Right, so these are going to be the Kahoot questions and also the midterm that eventually get to you guys. Some of these questions are going to show up on the midterm, so it's relevant to what we're doing now and also what you guys are going to see in a few weeks for the midterm. All right. Anybody else going to log on here? Got all our players. All right, and let's go. All right, rotational mechanics. Torque. What is torque defined as? Force times lever arm. Okay, you guys remember the last lab that we did for 2 days? That was torque, right? Right here. Let me switch my screen over here and remind you guys what torque is. Okay. So that's this right here. Okay. You guys remember if you're like using a wrench to turn a nut?
Faculty and students, at this time, the drill has been concluded. You may resume normal class and building 1 may come back to the building. At this time, the drill has concluded. Thank you for your participation.
Right. To say this is rusted over, it's really tight. It helps to push as hard as you can push. It also helps to push at the far end of the handle so you can increase this radial size. And it also helps to try to make this force and this lever arm at 90 degrees to each other, right? Want all those? Okay, all those will help you out, right? So that's R cross F, also called RF sine theta, right? Force times lever arm, that gives you torque. Same idea with opening a door. If you look at a door from a bird's eye point of view, this could be the hinges, this could be the handle, right? Same idea. All right, so let's flip back over here. All right, so somebody got that. Now somebody pick mass times velocity. Because mass times velocity, what does that represent in physics? You guys just had a quiz last week on this. Momentum, right? Yeah. If you said momentum times radius, that actually is something that represents a angular momentum for a point mass. Right? They did force times time could represent an impulse, like a change in momentum. Right? But yeah, force times lever arm, that's your torque. Right? Who got that? Liam. Oh yeah, the points. Question number 2. It's easier to loosen a nut with a wrench. Yeah, there you go. All the above. Right. So larger force, larger lever arm, and also make sure that they're perpendicular to each other. Right. That's what the sine theta is about. There you go. All the above. All right. Got Liam, Cole, Evan, Kaylani getting points. If a football is kicked through its center of gravity, what will the ball do? Kick it through its center of gravity. All right. Yeah, it's going to move without tumbling and turning, move without rotation. So here's a football. Right, so we got this ready to go, and we're going to kick this thing. Here's the center mass right there, right? About. Right. So how could you kick this, and what would that cause it to do? If you kick it down here, if you apply a force like right there, is it going to start to rotate counterclockwise? It's going to tumble through the air that way. But if you kick it like right here, is going to start to rotate clockwise, all that way. But if you kick it right through its center mass, it's gonna boom. It's not gonna rotate at all. Just gonna boom. It's like a knuckleball. Ah, Liam on fire. The resistance an object has to changes in its rotational state of motion. Ooh, somebody got it. All right, so rotational inertia. Okay, so I flip over here and remind you guys what that is. So I've got a whole table of rotational inertia values. Right? This is also hanging from my ceiling back there, right? All these posters, well, almost all these posters are, right? Okay. So suppose you set some rolly objects on an incline, let them roll down. Okay. You guys remember that these roll down at different rates, right? So somebody's going to win this race. Looks like the bowling ball is probably going to beat all these other rolly objects, right? But it's still going to lose to the thing that doesn't rotate at all on the friction length. Okay? But there's some friction here to do some rolling. Okay? And hey, why is this ring losing the race? Well, because it has so much rotational inertia. Right? It's really hard to get it going. Oh, here, it doesn't. The ring have the full mr squared, but all these other things have some fraction of mr squared, which means they have less rotational inertia than the ring. Okay? You guys remember these meter sticks that passed around? I have two of these, right, with the weights taped. Now this one has two weights on it. There's one of them. Right, and the other one's taped on the other end. The other guy here has the two weights taped in the middle. Okay? You guys remember this one's really easy to change this rotation because it has very little inertia in a rotational sense. But the one with the weights taped far out is kind of like this guy, right? Okay. So if I put those two meter sticks on hula hoops and I let those also roll down that same incline, where's that incline? There you go. Okay. Wouldn't the stick with the weights far out on the hula hoop look a lot like this? And the ones where they're close together look closer like this, right? So we got this versus this. So it has a lot of rotational inertia. It takes forever to get it going, but it's also really hard to stop. Okay. Rotational inertia. Liam, getting more points. Oh yeah. Which has more rotational inertia, a bike wheel or a solid disc? Same mass, same diameter. We'll stop this one in about 30 seconds here. Yeah, the wheel has less rotational inertia. Or sorry, more. The wheel has more rotational inertia. The disc has less rotational inertia. Right. So the ring would have more rotational inertia. Okay, let me flip my screen over. Remind you guys why that's the case. Okay. So we're comparing these two basically, right? Each rotating about like this type axis. Okay. Right. Actually, it should be like a 2-to-1 ratio. I mean, if they're the same mass and same radial size, wouldn't the ring have twice the rotational inertia of the solid disc in that case? I've got another question for you guys. I'm going to draw some bicycles here. Okay. You guys know a standard size bicycle wheel? Now, they come in different sizes, but most of them are what diameter? Like 26 inches, right? 26-inch diameter. Okay. But they're not all the same. I had a bike at one time that had like big old like 29-inch diameter wheels. I'm exaggerating the picture, but you guys get the idea. Hey, this diameter was like 29 inches. Okay. Now this one, which one of these, the top bike or the bottom bike? Which one has more rotational inertia? Yeah, the bottom one, right? Now they're both some version of this guy, right? Like most of the mass that tires like in the rim, like maybe there's a little bit of spokes, but it's pretty close to this, right? MR squared. Even if they were the same mass, which that's probably not even exactly true, but even if that were true, just the radial size alone would mean that the 29-inch tire has a lot more rotational inertia. So you can definitely feel it. Right? If you hop on both bicycles, right? This one you get it pedaling, it's like, okay, it takes certain resistance to get it going. Right? This one, it's a lot harder to get it pedaling. But I'll tell you what too, like once it is pedaling, it's a lot harder to stop it too. Right? It's a lot easier to like roll up on curves if there's like a big old curve here. Right? This one, well, also because of the radial size itself, right? Like it's like, it'll stop the bike. This one's it'll just like roll up on the curve. A lot more rotational inertia. Who got those points? Oh, Cole getting some points. Which has more rotational inertia? Runner who runs normally, say you're bending your legs, or say a runner who's like keeping their legs straight. Okay, so more rotational inertia, right? Like more resistance to change in motion would be like if you kept your legs straight. Okay, yeah, sort of like draw these. Okay. So if you're like bending your legs as you're running, okay, that's like this guy here. Okay. Versus say somebody's like just keeping their legs straight. They're like, like really derpy run. Okay. Okay. Well, this guy here is in a center mass. Like if you look at the center mass of his leg compared to the center mass of him, right, that's a really small radial distance. Versus this guy, his center mass and center mass is like, ooh, that's like a longer type distance. Right. You know what that also sort of reminds me of is, okay, you guys remember the figure skater here, ice skater? Okay. See, like if your mass is distributed far out, you have a huge rotational inertia. Versus anytime you like bring your center mass, like all your mass parts are getting closer to your center mass, that's like a smaller rotational inertia. Okay. Consistent with like this versus this, right? Same idea. All right, Cole and Liam, more points. A solid cylinder rolls down an incline with a greater acceleration than a hollow cylinder if what? Oh, yeah. So none of those conditions are necessary. Right, so wait, flip over back over here. Right, so where's right? So you guys remember like this roll race? Right? So I'm saying like the ring would lose to all these other rolly objects because it has the most rotational inertia, right? So it's hardest to get it going. Right? Although, of course, once it is going, it's also hardest to stop it. But that aside, it's still going to lose the race. Right? But hey, does that depend on the mass and the radial size? Like, is that controlled for? And whether it is or not, it turns out it doesn't matter. It just matters the distribution of mass. I can sort of show you guys that, right? Right here. So I've got a couple slides that show a basketball rolling down an incline. Right, so I know it's only one of the objects, but here's the point that I want to show you guys. Okay. Right, now, this way I solve it with conservation of energy. The question could be like, how fast is it going? Bottom was its linear speed. Point a radar gun at it. What's linear speed? So one way to solve it is like this way, right? So it's got potential energy at the top, and then at the bottom it has kinetic energy, but it's two types. One is like translational kinetic energy, and the other is kinetic energy that goes into its rotation. Okay? Sub in some values and solve blah blah blah. That just cancels out, and you get this expression. And what I want you guys to see here is that the mass of the basketball ended up canceling out. Right? I don't see an M anywhere in this expression. And also the radial size of the basketball cancel out too. So if you put a basketball next to a ping pong ball, I bet they would roll down side by side all the way down. And that's also true for all the other rolly objects. So if you put a marble next to a bowling ball, those are both solid spheres. I bet those would also roll side by side all the way down, the marble and the bowling ball, because the mass and the radial size end up canceling out. So it just has to do with the distribution of the mass, whether it's like a solid sphere or a cylinder or a ring. All right, got Liam, Cole, Evan, Kaylani. What's the point? A gymnast moves from an extended position to a tuck position. Ooh, that reminds me of the ice skater too, right? You go to a tuck position. Yeah, you would be decreasing your rotational inertia. And if you were rotating at the same time, you would also be increasing your angular velocity because angular momentum is conserved. Okay? So that's really similar to this. I mean, replace the gymnast with an ice skater, you have basically the same idea. Right? So going from left to right, you're taking your mass and bringing it in towards the axis of rotation. That's decreasing the rotational inertia. Right? So a bunch of guys got that. Okay? And if you're rotating at the same time, you go slow here and then really fast here, increasing your angular velocity because angular momentum is conserved. Left to right. All right, lots of points. Capri on the board, Liam on fire, in the lead. When an ice skater pulls it hands in to turn faster, what's true? Yeah, all the above. Right, all those things are true. Angular momentum is conserved, rotational inertia decreases, and rotational speed increases. Right, so those are all true. Okay, flip the screen. You guys can see this one more time. Right, that's that right there, right? Right. Angular momentum conserved, bam. Rotational inertia decreases, bam. Angular velocity increases, bam. Right? A, B, C, all the above. All the above. Wow, Liam's still on fire. As a large rotating cloud in space shrinks in size. So look out in space, see a big old nebula full of space dust. Right? Rotates a little bit, starts to gravitate closer. Yeah, it's going to spin faster, faster, faster. Isn't it the exact same idea as the ice skater? Right. Pulling their arms in, they speed up spinning. And because angular momentum is conserved, right, you have to speed up spinning, you gravitate in. Lehman first, Evan and Cole, second, third, Capri and Kaylani, rounding out top 5. When somebody leans to the center of a seesaw, what will that person's end of the seesaw do? Ooh, okay, most of you guys have that. Okay. Will rise. Now, why will it rise? Draw this for you guys here. All right, so we got the seesaw. Say we got a couple of friends. This guy's here, this guy's here. Okay. Maybe they're like equal mass and also equal distance from this pivot point. Right? So they'd be causing it equal torques. Okay. So if I treat this as the pivot, then this guy on the left is causing a counterclockwise torque. This guy on the right is causing a clockwise torque. And those should be balanced out. Okay, so it's all fine and good. Okay. But what if leave this guy right here. What if this guy like leans in? And you might I'll exaggerate that a bit. Usually if you exaggerate variables, help make it a little bit clearer what's going on. You might have this guy like walk in a pretty good distance. Put him like right here. Now they're the same mass, same weight, none of that changes. What does change is the torque value. It's not the guy on the right, it's the same torque as it was before. Okay? But you guys know that torque is equal to R cross F. So yeah, same force, same weight. But this radial size went from large to really small. So now it's only a tiny counterclockwise torque. And if it's only a small counterclockwise torque and the same clockwise torque, yeah, this whole thing's gonna wane like that. It's gonna exactly what you guys saw. All right. To turn a stubborn screw, it's best to use a screwdriver that has a, no, this is not a wrench, this is a screwdriver. So careful about that. Screwdriver. Oh, yeah, a wide handle. All right, all right. So draw this out for you guys. Make sure you're following here. Okay. So I got the screw. Let's draw a screwdriver. So like this. All right, and then handle on this guy. Right. So I'm trying to turn the screw. Really stubborn screw. Right. Now, I remember for the wrench, I cared about having a long wrench, but that's not true for the screwdriver. I care about having a wide screwdriver, and you guys got that. Because here's your radial size, and well, actually, I should draw it this way. Here's the radial size. I mean, that would also be true, right? But I'm going to draw a force because I'm putting a force on the edge, right? So this R crossed with this F. Okay, so I'm like, sure, try and turn it that way. That'll give me a torque. Torque equals that R crossed with that F. R cross F. There you go. Yeah, so you want a wide handle. Wide handle. All right, Cole moving up to second. Liam keeping the lead. A ring and a disc roll down a hill together. Which reaches the bottom first? Ring and a disc. Yeah, the disc, right? The solid cylinder is going to beat the ring, right? Every time, regardless of the mass of the weight, and also regardless of the radial size, because it has to do with the distribution of that mass, right? So the ring is going to have more rotational inertia, say like in proportion to its mass, radial size, whatever that is, right? Yeah. So the ring is always going to lose this race because it has the most rotational inertia out of all those objects. So the disc would win. Solid cylinder on its side would win. Cole on fire. William still in first, 10,000 points. Good explanation of why a ball gains speed as it rolls down an incline involves what? Yeah, all the above. Those are all true. See, force acts on it, a friction, and also a torque, right? So one of the important forces is its weight. Now, some component of its weight makes it roll. Right? But you know what? Here, you guys see this blue option, friction? What if there was no friction? Would it even roll at all if there was no friction? No, it wouldn't. It would just, it would look really weird. It wouldn't roll, right? So you need friction to induce the rolling. Now it'll be static friction, so it won't actually be taking energy out of the system, as long as it's not sliding. And that will allow for a torque to set up. Right, so flip the screen over here. I've got a couple slides that are same story, just different points of view, right? So here's the basketball rolling down. Here's a force acting on it, right? So there's a friction force here, and there's its weight acting here. The fact that those are two forces acting at different locations on the ball, right? One center mass, one surface, okay, sets up a torque, right? And then right, run the numbers, you get like this would be the speed at the bottom if that was what you were solving for, right? And then earlier today, I showed you guys a different point of view, conservation of energy. You get the same answer, the speed of the basketball at the bottom. Okay. All right. At different orientations, the cams provide different what? Actually, you're pulling on that one on the right. There's a rope right here. Feel all wonky. Yeah, there you go. Yeah, so the lever arm would be changing, and so with the forces and the torques, and if you wanted a constant torque, you'd have to change the force. So yeah, have to be a really weird wonky. All right. Points for everybody. Oh yeah. You guys remember the spool? Right. Suppose there's a floor right here. Right? You guys see the floor right here? I forgot to draw that. So you're pulling it towards you. So which way does it rotate? towards you. Right? You guys remember spool? I pulled it out. Okay. I think I got it here on the shelf. You can try that too. Coal on fire, leave it first. And then I changed the orientation of the string. Now there's still a floor down here. And you're pulling to the left. Which way does that thing roll off? There's a floor down here. There's a friction. There's a point of friction right here, right? Oh, one winner. Curious to see who got that, but gotta draw this out for you guys. Okay. So, wait, where is that? Here it is. I'll do this for you guys again. Okay. You guys can see this. Okay. Okay. So, you guys see I got inside radius, outside radius, right? I see that. Okay. So a couple questions ago, it's like, what if the string's on top like that? Right, pull that. Oh, it goes to the left. It's going counterclockwise. Okay. What if I put this whole thing upside down? Okay, and I pull to the left. Does it still go to the left counterclockwise? Yeah, it sure does. Okay, just like that. Okay, and side view. Okay, why is that? What's one explanation? Okay, so I got a point here where there's some friction. Okay, and I'm applying a force right here. She's ruler. Force, got a lever arm, R, right? So it's gonna rotate counterclockwise. There's a torque like that. Okay, that's it. Liam, getting the points. Where should a 30 Newton weight be placed so that the meter stick is balanced at the midway mark? So you want to balance that out. Where do you have to put a 30 Newton weight? Ooh, okay, a couple of guys got it. So flip the screen over. Okay. Yes, just did a whole 2-day lab that looked pretty similar to this, right? Okay, so I got this meter stick set up. There's a 20 centimeter, 30 centimeter, 40 centimeter, 50 centimeter mark. Okay. There was a 30, or no, sorry, there was a 10 Newton weight here. Right? Wasn't this pulling down with like 10 Newtons of force? Right? Now, if you treat this fulcrum as the pivot point, which is probably the most intuitive point, and also whatever upward force just zeroes out in terms of the torque, so that's the best point to pick. Okay? Then, and you guys remember, torque is equal to R cross F. Then isn't the radial size 30 centimeters? Right, I should have asked you guys, but guys, what's 50 minus 20? That's 30, right? You guys see a radial arm of 30 centimeters, right? And a force of 10 Newtons. So that's 30 centimeters times 10 Newtons. 30 centimeters, 10 Newtons. Isn't that 300 Newton centimeters? Or if you like, you could call it 3.0 Newton meters, right? Like your guys' lab. Right, so that's causing definitely a counterclockwise torque. Well, we want to balance that out. So we need another torque. And they gave you a 30 Newton weight. So I've got 30 Newtons, right? And if you hang it right here at the 60 centimeter mark, right, so it's right at the 60 mark. Guys, what's this radial arm right here? What's 60 minus 50? It's 10, right? Okay. So now you got 10 centimeters, 30 Newtons. Wouldn't that give you the same torque, except it would be clockwise instead of counterclockwise? Right? So that would balance it out, right? I figured that out. Capri and I missed who else. But all right, got Liam in the lead, got Cole, Evan, Capri, Kailani. In order to increase your rotational inertia, a tightrope walker should carry a long stick. most guys got that. Right now, why would that be true? Flip over here, show you guys. Okay. Say I got a couple of cliffs. I say cliff here, and then there's like a valley below. Okay. Right, I'm gonna have a tightrope going from one side to the other, and let's have a tightrope walker right here. Okay. So really hard to maintain your balance, but you know what could definitely help is if you carry a big old pole with you, really long pole. Right? Because wouldn't that give you a huge rotational inertia? Hey, do you guys remember like trying to balance a pin on your finger? It's like nearly impossible. But if you do that with a meter stick, right? Meter stick. Right? Oh, yeah, you guys could balance a meter stick, right? Because there's like it's so long, there's so much rotational inertia. Okay? So that it's really hard to topple over. Yeah, so this guy's a lot safer carrying the pole with him. All right, and last question for the win. A short pendulum has more rotational inertia than a long pendulum, say mass? Is that right, or is that? Right, everybody got that. All right, false. See, just for the recording, show you guys why. Let me find my rotational inertia table. Here we go. Right. So, see, mr squared, and for a point mass, which is going to be like a pendulum, just take this turn at vertical, it's just mr squared. So let's draw this out. A couple pendulums going. So I got a short pendulum versus a long pendulum. Okay. I equals mr squared. Okay. So a small r versus, I'll call this 2r. How about that? That could be r and 2r. Looks pretty close to you. Okay. Hey, how much rotational inertia would the long one have compared to the short one? It's not twice as much. How many times as much? 4. Because it's a factor of 2, isn't it? So twice the radial size being squared. Factor 2 squared is like 4 times. I bet whatever the rotational inertia this is, but this is 4 times that, right? Sure. All right, let's go to the winner's podium. For Kahoot. With the bronze, Evan. With the silver, Cole. And the gold, Liam. Runners up, Capri and Kaylani. All right, nice job, guys. Nice job, right there. All right. Good. We got a few minutes. I'm going to play you guys a. Here, let me find it. Play you guys something here. Pinewood Derby car. Here, flip my screen here. Okay. So suppose you want to send a Pinewood Derby car. Wait, did I tell you guys about Pinewood Derby car? Did you talk about this? Okay. All right, so you can buy this car in the bot. Well, you buy the wood body. You have to cut it, sand it down, put the wheels on. Okay, and you want to win this race from top to bottom. Okay. Now, how can you win the race? So he goes through this really long video. I'll play what well, we got about 5 minutes here anyway. Okay. So how can you maximize your chance of winning this race? Here's one perspective. This you can do conservation of energy. Actually, it is an open system. This would be the initial energy minus the work done by friction. You end up with some energy at the end. What type of energy at the top? Is it all potential energy, MGH? Okay. Minus the work done by friction, that could be force times distance. And if you wanted to, that friction force could be this expression, right? And then you'd be left over with some kind of energy at the end. You have kinetic, like linear kinetic energy, translational kinetic, that's 1/2 mv squared. And then also, aren't the wheels rotating? Do you think some energy goes into making the wheels rotate? So that's like 1/2 I omega squared. Now, if I is one wheel, the rotational inertia of one wheel, you might have like 4 wheels on the tracks that throw a factor of 4 in there. Actually, one of the tricks he says in this video is that if you lift one of the wheels off, you like bend the axle so only 3 wheels are rotating. This 4 turns into a 3, which gives you more energy to turn back into translational energy. And all the cars that win the race are all the ones that do that, just on 3 wheels instead of 4. All right, so I will play that out for the few minutes we got left in class. Oh, whoops. Okay, and that'll be a wrap on today.